Hi, folks. I'm Michael Black, and it's my pleasure to be here today and talk about retail vision at this workshop. And I'm sorry I can't be there in person. It's actually the first CVPR I've missed in 30 years. And I really wish I could be there with you and enjoying New Orleans. So, but my video presence will have to do. Unfortunately, I'm not yet an avatar, so you're going to have me in real life, a real recording here. But I want to talk about some work in my group on avatars and what I think that means for meta-commerce. Now, maybe meta-commerce isn't a term that a lot of people are familiar with yet. We all know regular old commerce. So here's a woman buying some clothing in an actual store, touching it, trying it on, etc. And we're all familiar with the e-commerce version of that, which is kind of a poor approximation. I can't touch things, I can't try them on, I don't know if they're going to fit, and a lot of people don't like buying clothing this way. So what's meta-commerce? Well, of course, it implies something about the metaverse, and what will commerce be like in the metaverse? So this is an example from Instagram. It's a partnership between Forever 21 and Roblox, the video game, and Roblox has been a real pioneer in metaverse kinds of applications. And what you see here is a woman who is wearing various clothing from Forever 21, and her Roblox avatar is dressed in the same clothing. Now, this is something that's called twinning. You have a twin of your clothing in the real world and your clothing in the virtual world. So what's important here? Well, there's a number of things in this very early video of what the meta-commerce is going to be like. But there's several, the key things are really a blurring between the physical and the virtual. So this Roblox character appears in the real world in a augmented reality kind of way in the apartment of this young woman. And the avatar and the woman, even though the avatar is obviously not designed to be a physical likeness of her, they share various characteristics, hairstyle, overall build, maybe facial shape, and a few things like this that connect her with her avatar. The customer and the avatar are wearing the same clothing. And the interesting thing here is, of course, you can buy this clothing in both the physical and the digital worlds. And in fact, there was an interesting crossover. People were selling, Roblox was selling Forever 21 beanies, and then they were so popular that Forever 21 made them in the real world. So people could buy them and have them in both the real world and on the virtual character. And this is the real exciting point, I think, for meta-commerce. And one thing that's key here is that 3D avatars are playing a central role. Okay, so the game character here is not a very realistic avatar, but it's 3D. And that's important because it can be embedded in the 3D world of the owner, in a sense, of the customer, blurring that boundary between the physical and the virtual. And there's another key thing here, which is that it's designed to be a fun experience. So these are, I think, some of the unique principles of meta-commerce that distinguish it from the previous e-commerce phase that we've been in for a long time. So I argue that this age of avatars is coming, and what do I mean by that? Well, I mean that the avatar will be everywhere and a key enabler of the metaverse. Now, I have to define for you what I mean by avatar, of course. What people mean all kinds of different things, from fun Roblox-like game characters through to fully realistic digital twins, replicas of a person that are photoreal. But I think it's neither one nor the other, it's all of those. People are going to want all kinds of avatars for all kinds of things. They're going to want maybe a fully realistic one for digital fashion and fitness and health applications. For training AI algorithms, we want synthetic data that's fully realistic. But in games and entertainment, we might want to choose other kinds of more fantasy or cartoon-like characters. And then in augmented and virtual reality, we can be whoever we want, but in augmented reality, we also have to kind of connect with the physical and the real world. We may want to augment our bodies or the bodies of other people. So that ties us to this physical realism. Regardless of the physical form, whether it's a toy or it's realistic, it's got to move like a real person. It's got to interact with other avatars and 3D scenes, maybe in an augmented reality case in the actual 3D world. It has to plug and play across these applications. The metaverse is not going to work if everything is siloed and your digital fashion avatar doesn't play well in virtual reality or your fitness app or your games, right? There needs to be a common kind of platform so all these applications can talk to each other. You know, imagine the internet if it was siloed into different areas, it wouldn't have worked. And so it has to. The other thing is it has to work with computer graphic systems of today, whatever we build. It's great to think about the future, and we definitely should, but people want these things to work now with the tools we have today. So the problem for doing this is there's just really too much friction. It's time consuming to create an avatar. These avatars aren't portable. The whole process doesn't scale. So what we've got at one extreme, we've got things like 3D scanners, which are accurate but expensive, and who has them? I have one, but I have several, but most people don't have any. You'd think, well, maybe these LiDAR scanners on phones are solving the problem, but if you've ever looked at the data, it's actually pretty noisy, and it's very hard to scan a whole body, for example, to create an avatar. So most creation methods that try to create a realistic avatar use some kind of video capture app on your phone where you have to put on tight-fitting clothing and take a particular pose and move very carefully and follow instructions. It's not the kind of thing you can do in your cubicle at work. You don't have the right clothing. It's time-consuming, and users don't really follow instructions. They never listen or read. So, the whole thing doesn't really work very well. It's a big barrier. And so most of the time, the avatars people create are these sort of fun, goofy, unrealistic things where you can pick your hair color and so on. And that's where we are today, but I don't think that's where we're going to be in the future. I think we're there today because that's the low friction way of creating avatars. So what we really need is a low friction way of creating your digital double, something much more like you. And so just some example of work that we recently published at 3DV called Pixie, which takes an image of a person and reconstructs their 3D body, their facial expressions in relatively good detail, really captures both hand poses and something expressive about the body. So that's what we'd like to move towards, but even better than that. And the foundation for all of this is a 3D virtual human. So what's a 3D virtual human? It's a simple mathematical model of body shape. It should look like a real person. It should move like a real person. It should be compatible with standard graphics tools, so it's portable across all platforms. It should be able to interact with people and scenes, so it should have facial expressions, gestures. It should be able to contact the world, a virtual world, and it should also model clothing, though I'm not showing that here. So from several years ago in 2015, we introduced a model that's become popular called Simple, which is a skinned multi-person linear model. Many of you probably are familiar with it, so I won't go into details, but the basic thing is it's a function M. It takes pose parameters theta and shape parameters beta, and it uses, it's portable because it uses linear blend skinning. W is a linear blend skinning function, which is common in graphics, that takes some arguments and produces vertices of a watertight mesh. The arguments it takes is a template mesh, which is a function of the body shape and pose, some joints, which are a function of body shape, some blend weights, which are learned in the pose of the body. And this whole, the key of Simple was, well, one, it was built on linear blend skinning with these little additions, but the key thing is that everything was learned from thousands of scans of real people. And that meant that it could really be accurate and model the body well. But the problem of really capturing humans and in all their glory is a challenging one because humans are complicated. We have varied body shapes, for example. We wear complicated clothing in layers. We move in complicated ways. We gesture with our hands. We emote with our face. We communicate with each other to reveal something about ourselves that's important. We contact our bodies in ways that make computer vision challenging, but for support, self-support, and also to communicate. We interact with objects in the world, a huge variety of them, and we don't just grasp them with our hands. We use our whole bodies in interacting with objects. And we don't just interact with objects, we interact with each other through social touch, handshakes and hugs and kisses and so on. So understanding human bodies and their interactions, and then recreating them in avatars is a massive challenge. And I won't solve it for you today, but I'll take you on a little journey of where we were and where the field is now. And I'll blatantly plug a few CVPR papers that we have so that you can go check them out. So I think the first breakthrough in estimating an avatar from images really came with Anju Kanazawa's work in 2018. And this is a classic now. This is how many things work. You take a cropped image region around a person, it goes into some encoder, like a ResNet. There's a neural network that then regresses pose parameters, shape parameters, and camera parameters. Typically the camera is just scale and translation, not perspective, though that varies. And then it outputs the parameters of a simple model. Using that function M, we can reconstruct the 3D body, and using the function J, which takes the body parameters and gives you the joints, we get the 3D joints of the body. And then those get projected into the image, given the camera, and then we get 2D joints. Now, there are lots of data sets in which people have gone through and labeled the 2D joints in the image, so one can just write a simple L2 loss on the difference between the observed 2D training joints and the projected ones, and you could minimize that. And by the way, Anju's, one of her key insights was to iteratively regress these body parameters. But anyway, if you just do this, you end up with what I call monsters. You get body shapes that really don't look like the person in the image, even though they minimize this 2D joint error. Okay, so that didn't work. And so Anju had another great idea, which was to use discriminative training. So here we have a data set of lots of people. We know a lot about body shapes and poses. So if the regressor produces a body that doesn't look like a body that we know to be a true human body, then the discriminator will learn to detect that and reject it. And so training this all together, the network actually produces good results. So that's, all the way back in 2018. Where are we now? So I'll just give you some teasers for current work. So we have a paper called BEV, which stands for Bird's Eye View, called Putting People in Their Place, Monocular Regression of 3D People in Depth. And Yu Sun is the brilliant student who's been doing this work. And the whole idea is to break away from this idea of detecting bounding boxes around people and then processing all the bounding boxes in a multi-step paradigm. Instead, we just want to process the whole image at once, and we want to estimate all the people in the image in one shot and put them all in depth. And we want to do this all, train this all end to end, and we want this to work regardless of the age of the people in this picture. So here we have kids and adults, for example. So the previous methods, this is just an example from Vibe, all do bounding box detection first, find all the people, and then you process them. In cases where people are overlapping, however, things can be really ambiguous. The other thing is when you crop out these bounding boxes, you no longer get to see the whole scene. And so you lose all the scene context that could tell you a lot about what's going on. So these methods tend not to be very robust, and they're completely dependent on how good the bounding box person detector is. So we've been focusing there's a couple papers, ROMP and now BEV, that are simple one-stage frameworks. ROMP is real time. It estimates all the people in the scene, and it's robust to occlusions. So here you see some examples in the dotted boxes where the bounding boxes have people occluding each other, and these end-to-end methods do better there. So just briefly, what did ROMP do? This was from ICCV last year. ROMP takes the whole image in and then has these 3 heads that produce different maps. The first one is a body center heat map. This basically is telling you the probability that there's a body centered at a particular pixel, and you see little heat maps there on the top. And then there's a mesh parameter map, which basically says at each point in that body center map, if there's a body there, what are its simple shape and pose parameters? Okay, so we store those there. And then there's a camera map. And then you can sample from the body center heat map, get bodies, and then with their simple parameters at every image position and project them into the image with the camera information. Now, that worked pretty well, except that center heat map is a heat map in the image plane, and it doesn't know anything about depth. And so ROMP doesn't do a very good job of putting people in depth, as you can see on the left here. And another recent method, CRMH, also has problems that people are the wrong size and they're in the wrong depth order, even though it reasons about depth. But BEV, we introduced an explicit 3D representation. Now, doing inference in a full 3D representation is complicated, so we have a little trick for dealing with that. Another problem with existing methods is they all use the simple body, which is just for adults. And if you see a child in an image and you assume it's an adult, then it's a very short adult. So the only way to make that plausible is to make it a regular size adult, but put them far away. So, and so that's exactly what you see here with ROMP and CRMH. This lineup of kids, from small kids to teenagers, you see that instead of being in a straight row, they're all slanted in depth. But BEV estimates infants, children, teenagers, and adults, and manages to figure out that they're all in a line, just different ages. So how does this all work? The first trick was to begin reasoning in 3D. So remember, ROMP takes in an image and creates a center heat map aligned to the pixels in the image. Well, with BEV, we introduced an imaginary bird's eye view. Just imagine there was some camera, which we don't have. We just have the front view. But imagine you had a camera looking down and could look at where all the people are. You could also try to estimate the heat maps from above, and that would put the people in depth. And so BEV is going to try to do that. It's going to try to estimate the front view and this bird's eye view that it doesn't see. Now, you might say, well, you could just estimate all of this in a 3D volume, and we did try that. It's a lot more parameters, it's a lot more complicated to train, and it doesn't converge as well. So this is exploiting the idea that these are separable representations. And the other key idea is to use a weakly supervised training scheme. And we do 2 things there. We introduce training data about ages of people. We also introduce a version of simple that can represent infants, children, and adults. And we also have weak labels on depth ordering that we exploit during training to train the method. So just quickly taking you through that, the way BEV works, it takes an input image. It looks a little bit like ROMP here. We have body center heat maps. There's offset maps that refine that, and then a mesh parameter map. And then what we add is this bird's eye view representation, as well as offset maps for the bird's eye view. The front view and the bird's eye view can then be composed into a full 3D representation. And then we can reason about that 3D center map. But training it this way works better. There's also a camera map that's a little bit like ROMP, and an 3D offset map. these things all get sampled from, allow us to estimate the translation of people in depth. We then can sample the feature map, and we can compute the depth ordering and put the body shapes in depth. And the losses we use here, there's a L depth is this weak depth ordering loss, and L age is this loss about ages of people in a training set. And for people of different ages, we have ranges of their possible heights. So to train all that, we needed a data set. So Yusun created this relative human data set that supports in the wild monocular human depth reasoning. He has weak annotations with depth layers. Here, this sports team, Frisbee team, the blue people are in front in depth layer 0, the yellow are in depth layer 1, and then there's a guy in gray and yet another depth layer in behind. And so this is just a weak labeling of depth layers. And then we also, here on the right, there's an image in which the people are labeled in the depth layers. They're all in the same depth layer, but different ages. There's it says teenager here, maybe it looks more like a child, a baby, and an adult. And then we designed losses to take into account these things and an expanded simple model. So let me just show you some results. Here's an input image. CRMH estimates a bunch of adults, so it gets the children wrong, and then of course the depth ordering wrong. ROMP also does the same thing, but gets different depth ordering, but BEV actually does something sensible with the children and the spatial relationships. We don't have any reasoning about interpenetration, by the way. A few more examples, people lined up. I like this one of the royal family because you got a bunch of ages and the spatial relationships are roughly right here. Just a crowded scenes like this. Again, there's no bounding box detection here. It's just a one-shot method that produces all the bodies at the same time and their depth relationships. Here are different ages again, and roughly correct depth relationships. And I like this one because it works on grayscale images from the old days. Anyway, so that's where we are with estimating people from images. Now, there's something really missing here. You'll notice that the body shapes, apart from now we can deal with ages a little bit, they're all pretty generic bodies. Basically, the current state of the art, most of the methods estimate something like an average body shape. So we have another paper here called SHAPY. This is the very first talk of the conference in the very first oral session, so please don't miss that. It's on accurate 3D body shape regression using metric and semantic attributes. And the idea here is, for many applications, particularly in the retail space, we want accurate body shapes. And we want to reduce friction. We don't want people to have to go to scanners and have lots of measurements and so on. So how do we do that? Well, if we had paired data of images in the wild, like the image on the left, people in arbitrary clothing, and we had ground truth 3D body scans for this, or simple model parameters, then we would just have a supervised learning problem, and we could train a network to regress from images to 3D body models. But getting paired data like that at scale, given the variety of people and clothing and so on, it's actually, that's a non-trivial task. So we asked the question, what could people label? Like, I showed you that the original work with Zhu, the HMR method, used hand-labeled key points, 2D key points. Humans are good at that. They can click a bunch of points. What can people do about shape? Well, they can't tell us, how much someone weighs and exactly what their waist size is. They're not good at that. But we do have words that we could use to describe shape. So our question was whether we could use linguistic descriptions of shape to capture the body. And this idea we explored in some earlier work in SIGGRAPH 2016 on a piece of work called Body Talk, where we showed that people do use language to communicate shape. And this means that we have in our heads some mental model of body shape in 3D that we can use to communicate. And here the model learned various things like for women, various words like feminine, long legs, pear-shaped, rectangular, round apple, and short were associated with these sort of prototype bodies. And we build a mathematical model of this. So our idea was, well, maybe we could use that same idea to train a metrically accurate body shape regressor using only linguistic descriptions of images. So that's what we're going to do. We're going to take images like the one on the left and have them rated by a bunch of workers on Mechanical Turk according to a variety of phrases like pear-shaped or muscular. And then we're going to formulate a loss that helps us train that. So to do this, we have to label two different types of data. We label 3D bodies, like the one on the left, which we have lots of different body shapes from the Caesar data set. They get rated on 15 of the top shape words from Body Talk. We average the ratings of a bunch of different raters. We also have the raters label image data, like the one on the right, with the same words. And they're not paired, right? We don't have the 3D scan of this woman on the right. This completely separate data set. So scan data set and an image data set, but labeled with the same semantic shape words. We do a bunch of stuff, and I'll refer you to the paper and the poster for details, the oral as well. But a key thing is something we call shape to attributes, or S to A. Given a body shape, say we regress this person's body shape from the image. Given the body shape, we train a very simple polynomial regression model to take the shape and predict the ratings that correspond to that shape. So for example, this person has broad shoulders. They do not have a delicate build. They have a long neck. They're masculine. They're muscular, very muscular. They're not short. They don't have a soft body, okay? So we train that on this scan data, this shape to attributes thing. Now, shape to attributes turns out to be the key player here, because what we're going to do is we're going to train a regression method, a little bit like the old Anjou method, except we're building this on top of expose, which was an earlier work of ours. You take an image in, you train a regressor to predict simple X pose parameters and simple X shape parameters. We take those shape parameters, we pump them through this polynomial model, shape to attributes, that gives estimated attributes for the regressed shape. And then we add to our loss, we have a standard training loss for 2D joints and all the other stuff you would normally do here, but we add a loss on the attribute values. The attributes of the estimated body shape should match the attributes that were labeled for this image. And that turns out to be enough to predict body shape, to basically ignore clothing, and to do this as a state of the art. So it turns out that if you have carefully controlled imagery with tight-fitting clothing, you could do better also by exploiting silhouettes. But if you don't have that, if you have sort of images in the wild like this, methods that use silhouettes get very confused by the clothing, and this approach, SHAPY, does really well. But I'm going to argue that we need even more if we want to be able to control our avatars and really feel like we own them. We need them to be emotional. And for that, we also need to capture the emotion of the users who are controlling or using their avatars. And for that, we have a paper called EMOCA, which regresses 3D faces directly from input image. It's robust. And the clever idea here, I think, is that it uses some side information. It's trained completely from images to estimate the 3D flame parameters, as well as detail parameters, detail shape. And what it does is it exploits information about emotion during the training. This is a poster on the 24th in poster session 4.2, EMOCA, emotion-driven monocular face capture and animations. Check that out. EMOCA is based on a method called DECA from SIGGRAPH 21, in which we have taken an input image, we encode the shape and the expression and some detail. We estimate the albedo and the shape. We combine all these things, we differentiably render that, and we produce an image, okay? And in the standard, we have standard losses in DECA that, look at how similar that image is to the input image. The novelty in EMOCA is this top bit, which is we add an emotion consistency loss. And that says, if we take an emotion recognition network that detects the emotion, the valence, and the arousal in that image, the emotional content of the input image should be the same as the emotional content of this rendered image that we are generating from the model. And so we formulated a motion consistency loss that encourages that. And the result is that this EMOCA method learns to produce much more emotional faces than DECA or the current state of the art. All right, I'm really just about out of time. I think I've got 5 minutes left. So all that's well and good, but there's still a problem. We've been working with these simple body models, which don't capture things like hair, clothing, shoes, and other personalized details. So to really, we're going to want these avatars like that case of twinning I said. We're going to want to dress them, and so we need something that's richer and more visually expressive. So we have a few papers here. I'll just point you to GDNA is a generative model of 3D clothed people. We have a distribution over people that we can sample from. We can pose them and change their body shape with simple parameters. They're not super realistic yet, but this is the first generative implicit model of clothed humans. So I encourage you to check that out on the 24th in poster session 4.2. Now, we have another paper on trying to create more realistic looking avatars using implicit representations of shape and texture and so on. And here's, this is work. This is an oral on the 23rd at 1:30 session in the afternoon. It's called I Am Avatar, Implicit Morphable Head Models. And Otmar is one of the collaborators. So he's talking about here. I don't know if you can hear this.
Hello, everybody. This is my test sequence. I'm Avatar. It's great.
He's basically, he can't really hear him, I'm sorry, but he's saying that I Am Avatar is great and it's the best thing at the conference. And so this is from a very short video clip. We construct, and I think I have a slide on it. For a very short video clip, we construct an implicit model that's really, it's like classic linear blend skinning used in 3D for the head. But we replace all of the pieces with continuous fields in a canonical space. So there's canonical continuous fields for geometry, texture, deformation blend shapes, and linear blend skinning weights. And behind this whole thing is the flame head model parameters, so we can actually control the head with head rotation, jaw pose, and facial expression parameters to generate new heads and even in extreme poses, and it's all learned from video. And then finally, we want to really create full body avatars from images, and we want to be able to do it from arbitrary images and arbitrary poses. So here, there's the results of ICON, which is on the 23rd in the morning in the poster session. It's the papers on implicit clothed humans obtained from normals. The blue is the rendering from the front, and the bronze is the rendering from the back. And you see that there's some pretty extreme poses here. So we could take images like this, where current methods fail, methods like PyFu and Arch++. These are great methods. They work really well on fashion images, fashion poses. They don't work well on these kinds of poses. But ICON does a reasonable job of reconstructing 3D shape from a single image of a person in clothing in crazy poses. So I think this is and from this we demonstrate that we can actually build an animatable avatar. It's not perfect yet, but you get the idea where we're going. We're trying to exploit the latest in implicit and neural rendering to create much more realistic avatars. So where's this headed? 3D avatars. The age of avatars, as I said in the beginning, is definitely coming. It's going to have a big impact on how we shop and how we play. Reducing friction in creating these avatars is key. We want to be able to animate them with user motions and facial expressions. This is what builds a deep connection with the avatar. They need to look more realistic than the ones we have today. They need to have clothing, shoes, accessories, and look like real people. And implicit surfaces, neural rendering, radiance fields, etc., are all progressing very quickly. Some of them have worked well for rigid scenes, and they're being extended to articulated and deformable objects like humans. So, and that's coming very quickly.
Get your avatar today. Here it is. I am Avatar. The best avatar out there, easy to make, easy to create, easy to control. It's you, only better, because you don't have to be there. So get your I am Avatar and get it now.
So there you go. That's not even me. It's my avatar talking, and hopefully it sounds believable. Thanks everybody for your attention, and I'm happy to take questions.